Lesson 4-5, Greatest Common Factor or GCF. And in this lesson, you learn to find the greatest common factor of two or more integers or monomials. Why is it important? Because you can use the greatest common factor when determining the amount of lumber needed for a project. Let's take a look at this example in history. Very little of the mathematics of ancient China remains known to us today. The Chinese recorded information on bamboo, which did not last very long. Also, many of the books were destroyed during the reign of Emperor Shi Huangti, but the Zhuzhang Suanshu, or the 9 chapters of the mathematical art, survived to tell us a great deal about the mathematical accomplishments of the culture. Okay, and in one of those chapters, okay, in the Zhuzhang Suanshu contains information on field measurement. In it, procedure for finding the greatest common factor or GCF of two numbers is described, and you will learn that when you get to exercise 40 in the classwork. We will also discuss that in class. Okay, we'll find the Chinese method or learn the Chinese method to find the GCF. But first things first, let's learn how to find the GCF. So the greatest of the factors of two or more numbers is called the greatest common factor. There are many methods for finding the greatest common factor. One method is simply list the factors of each number and identify the greatest of the factors common to the numbers. Okay, let's take for example 78 and 91. We want to find the GCF of those two numbers. We list the factors of 78, and these are the factors of 78: 1 times 78, 2 times 39, 3 times 26, and 6 times 13. Okay, those are all the factors of 78. And the factors of 79 are 1 times 91, 7 times 13. Those are all the factors of 91. And if you notice, okay, 1 and 13 are in blue, meaning they are the common factors of 78 and 91. But the greatest common factor of 78 and 91 is 13. So 13 now becomes the GCF of 78 and 91. Okay, now listing is a good method, but once the numbers become very big, okay, it is going to be a huge task to find the greatest common factors when you list them. So another way of finding the greatest common factor of two or more numbers is to find the prime factorization of the numbers and then find the product of their common factors. Okay, let's look at how we do this. Use the prime factorization to find the GCF of two sets of numbers, 315 and 135. First, find the prime factorization of each number. Okay, prime factorization of 315 is 3 times 105. 3 times 105, okay? And we know for a fact that 3 is already prime, so we simply bring it down. 105 is not. According to our divisibility rules, it ends in 5. That means it's divisible by 5 still. So that's 5 times 21. We know that 3 is prime, bring that down. Also, we know that 5 is prime, we also bring that down. 21 is not prime, so we continue factoring. 3 times 7, and now all of them are prime. Okay? And then we factor 135, okay? 135 ends in 5, so it's divisible by 5. 5 times 27. We know that 5 is prime, we bring that down. 27 is not prime, and we continue factoring. 3 times 9. We know 5 and 3 are prime, bring both of those down. 9 is not prime, get two factors of 9, which are 3 and 3. Okay? Then next, find the common factors. Okay, so you have 315. Okay, and this is the prime factorization of 315. 3 times 5 times 3 times 7. Okay, and 5 times 3 times 3 times 3 for 135. So the best way to do this is to arrange them from least to greatest. Okay, 3 times 3 times 5 times 7. And 3 times 3 times 3 times 5. And we circle our common factors. 3 is common to both, we circle that. This 3 also is common, we circle that. Okay, and the 5 is common, we circle that. as well. Okay, and then we bring them down once. Okay, after bringing the 3 down once, okay, we find out that the greatest common factor of 315 and 135 is 3 times 3 times 5. So we bring the 3 down once, right here. Okay, we bring the other 3 down right there, and we get that 5, bring it down right there. And we simply multiply those 3 times 3 times 5, and that will end up with 45. So the greatest common factor of 315 and 135 is 45. If you notice, these are huge numbers. So if you start listing the factors of these numbers, it'll take you a long time. Okay, let's take a look at example B. We want to find the GCF again of 3 numbers this time, 66, 90, and 150. Let's express each number as a product of prime factors. So let's do the prime factorization of 66. Okay, and the prime factorization of 66. Oop, not that one. We are going to lock that so it does not move for us. There you go. Okay, so the prime factorization of 66 is where is it? There you go. 2 times 3 times 11. Again, we use the factor tree, or we use the drop down method. Remember the drop down method, get 66. Okay, first prime number that goes into 66 is 2. 66 divided by 2 is, okay, 33. First prime number that goes into 33 is 3. 33 divided by 3 is 11. And we stop when the very bottom number is a prime number. So it's 2 times 3 times 11. Okay. Same thing with 90. We get the prime factors of 90. Okay, 2 times 3 times 3 times 5. And 150, we get the prime factors of 150. 2 times 3 times 5 times 5 times 5. Okay, so if you notice here, the common factors are 2 and 3. Why are they 2 and 3? Because if I get this, that'll be 2, and that'll be 3, and I simply bring them down once. So the GCF of 66, 90, and 150 is 6. Okay? Let's take a look at the next example. Real-life examples involving GCF. Shamika is covering the surface of an end table with an equal-sized ceramic tiles. Okay. The table is 30 inches long and 24 inches wide. What is the largest square tile that Shamika can use and not have to cut any tiles? And letter B, how many tiles will Shamika need? Okay, so again, this type of problem is a great GCF problem. So the size of the tile is the greatest common factor of 30 and 24. So we get the prime factorization of 30, okay, which is, oopsie, sorry, there you go, 2 times 3 times 5. Now I put the circle ahead of everything else. So 2 times 3 times 5 is the prime factorization of 30, and the prime factorization of 24 is 2 times 2 times 3, anticlimactic. So if you notice, I circled the common factors of 30 and 24, 2 and 3, and we brought it down once. So the GCF of 30 and 24 is 6, because 2 times 3 equals 6. So Shamika should use the tiles that are 6-inch squares. Okay, but we're not done. Letter B, how many tiles will Shamika need? So using what we know, that the greatest common factor is 6, we simply divide 30 by 6. That'll give us 5. And we get 24 divided by 6 will give us 4. What does that mean? That means that Shamika will need 5 times 4, or 20 tiles, to cover the table. Okay? So we answered A and B for this one. And let's do the last example, connection to algebra. So the product of the common prime factors of two or more monomials is their GCF. So if we are doing now uh, algebraic expressions, you want to find the GCF, this is how you do it. First and foremost, find the prime factors of 36, 2 times 2 times 3 times 3, and simply expand x cubed to become x times x times x and y right there. Okay? And 56, the GCF of, the prime factorization of 56 is 2 times 2 times 2 times 7. Okay? Using a factor tree or the drop-down method, x to the first power is simply x, y to the second power is y times y expanded. Okay? And after we do that, we simply circle the common factors. That 2 is common. Okay? Or I circle it, I think, because I did not make an effect on this one. Okay, I'll circle it. Okay? So this 2 is common. I'll circle that. This 2 is common. I'll circle that. This x is common. And the y is also common. And what you do next is simply bring down one of them, each of them one at a time. Okay? So you have 2 times 2 times x times y, or 4xy. Okay? And that is the GCF of the algebraic expression 36x cubed y and 56xy squared. Alright, that's the end of the lesson. Thanks for watching.